Hello everyone, welcome to the heat transfer experiment EMCH 361 lab 5 heat transfer. The topic is the measurement of two different materials, metal and non-metal. Metal, which is brass, and non-metal, which is a PLA. So the objective of this lab is to measure, to study the thermal conductivity of engineering material. The second objective is to find the thermal conductivity of brass materials. We are going to measure the thermal conductivity of brass materials by using arm film linear conduction apparatus. This arm film linear conduction apparatus. The third objective is to measure the thermal conductivity of PLA. PLA, which is polymer. We are going to use to find the thermal conductivity of PLA by using C-therm. So, in order to do this experiment, we are trying to understand the famous Fourier law, heat conduction, with the two equipment to find the thermal conductivity. The first equipment that we are going to use is called HT10XC, heat transfer surface unit. This is the power supply. We are going using this power supply to apply heat to run electric heater. There is an electric heater embedded here. There is electric heater connected to this power supply, getting power, electric heater that can apply heat to this linear conduction model. The second one, arm film linear conduction apparatus. We have this linear conduction apparatus. There is two most important layers. The first one is called hot layer. You have a clear picture. This is that I already explained in the presentation. Here the heater, the location of the heater on the top. This is the hot layer. Here the hot layer. And the specimen position, which is this one, 25 millimeter apparatus, sandwich between hot layer and cold layer. And the third one is called cooling layer. Cooling layer. This is the cooling layer. And there is a water, this cooling water inlet, cooling water outlet. The cooling goes from here, circulation, to make this surface, to keep this temperature constant, which is this temperature is almost the room temperature, which is 20 or 19, it depends on the room temperature. Right now I think 20 degrees. So we need to make sure there is a water goes in and out. If you shut down the water, the system will burn out. Burn out, it means this will burn out, will take maybe 20 minutes or 30 minutes or 1 hour. It depends on the power supply that you apply. So make sure the water go in and go out, circulation. And also there are 8 thermocouples that will use to measure the surface temperature. The first, this is the 3 thermocouples. They are labeled with number 1, number 2, and number 3. in the hot layer, and 2 thermocouples on the basement, on the brass materials, 4 and 5, and 3 thermocouples on the cooling layer, which is 6, 7, 8. 8 thermocouples that connected to the hot layer, basement, brass, cooling layer are connecting to the DAG. Here, this is the DAG. So this is the DAG, these thermocouples connecting to the DAG, and then from this DAG transfer to the computer. And there is a program inside the computer laptop. That program is showing the y-axis as surface temperature and x-axis at the time, and then show you how the temperature with the time versus time, because this test it depends on the power that you will apply. If you apply high power, for example, I already send you a text file. When the highest value of power supply 13.5 and ampere 1.38. This is take 30 minutes or 26 minutes to reach the steady state. I will show you how to show you the steady state, or how to reach the steady state. So I'm waiting the program to open. Here you can see this is the text file. This is the value, old value. We need to make sure. Control A, delete. Okay, this is the text file that we will use to save the data. It's the text file. So what I'm trying to do, I will follow the experimental procedure. First one, connect the power supply heat source to the main source. This is the power supply. I'm going to connect it. Yeah, this is, I'm connecting here, connecting to the power supply. Make sure this is turned off. And here, a manually remote. So we will use manually. I will keep it, make sure it's 0. And second, connect the power of heater to power supply. This is the power of heater to the power supply here, connecting to the power supply. Third, prepare the sample. And then after prepare sample, place basement between heat source and heat sink. This is the heat sink, we call heat sink, and we call the hot layer and cooling layer. So I'm going to use a thermal grease. The purpose of using a thermal grease is to increase the contact area. This thermal grease. By the way, you can see here, T hot face, T cold face. This is basement, this is T hot. T hot and T cold. We don't have the T hot and T cold. We have a thermocouple for 4 and 5. We will use interpolation to find the T hot and T cold to determine the thermal conductivity. So right now we place and use some thermal grease. Make sure close it. So let's add it. Right now it's rigid. Okay. The fourth one, we place the spacement between heat source and heat sink. Fix 8 thermocouples between the heat source and heat sinks and then connecting to the duct. So these thermocouples, 3, 2, and 3, which is all together, 8 thermocouples connecting to the surface temperature and then to duct. So we are, okay, it's connected. Make sure it's connected. And also here the label, the R label with the number is similar to the number here. So for example, number 4, here is number 4. Number 2, here is the number 2. So measure the distance between thermocouples. We need to measure the thermal distance between approximately I measure it and convert inch to milli, which is 15 millimeter. 15 millimeter. Okay. So distance 15 millimeter between two thermocouples. Turn cooling water on. Make sure the water cooling on. It doesn't matter if you make it more or less, but make it reasonable. There's water, should be there's water. Here, this is the cooling water. So right now we need to open CVI software. Open. They will ask me about the cooling water. So they ask me, you can see here, turn cooling water on. I already did. Yes. Have you saved the previous data file? Yes, I saved it. So right now, we will start. Before, I'm going to start right now, and there is no heat. There is no heat, and then you can see the temperature. The surface temperature is room temperature, 20. Once I added heat, it will gradually increase. You can see right now, just focus on this program. Focus here. This is the power. Make it 0. I'm going to increase the power. Increase gradually until we reach, I will add it 9.5. So the power 9.5. You can see right now power gradually increase. So you can see this is in power supply. This is T1, T2, 3, 4, 5, 6, 7, 8. We can connect these thermocouples connected to the power supply. It's okay, there's no problem. But when we need the value of surface temperature for T1, T2, 3, and so on, you need to change this. As you can see, T1, T2, T3, T4, and take a lot of time. So what you did, we create a lab view program, which is not me, a mechanical engineering department, create a program and with the DAC, and you can see here for arm film linear conduction, this linear conduction model, you can see a temperature linear. This is the highest one, this is the lowest one. You can see here T1, T2, T3, 4. Follow the number 1, 2, 3, 4, 5, 6, 7, 8. Right now, the temperature gradually increase. Once the reading of thermocouples reach steady state, the data record. I record the data from the beginning. And then after when it reaches, this is take at least 20 minutes to reach the steady state. What happens when we reach the steady state? It will this shown area, this will show me the surface temperature is constant. When you see the surface temperature is constant, there is no variation. It means you are reached the steady state, and then you can use this value, average this value, maybe 10, 100 value or 200 values, and then you can average. After that, you take this value for temperature, and then you can apply using heat conduction. The third objective of this lab is to measure the thermal conductivity of PLA, polymer, by using, this is the material that we are going to use it, by using a C-therm. So the idea behind the C-therm, a concept of using a C-therm is two most important equations, diffusivity and effusivity. And for effusivity, it depends on the square root of thermal conductivity of the material and density of the material and the specific heat. That will determine the thermal conductivity direct. You don't need to worry about the hand calculation or anything. You don't need to worry about the T hot and T surface, and this and also you don't need to do some preparation for the sample. Just you need to add this sample here on this. It's called modify transient plane surface, and there is a heater. You can see the heater. This one getting heat, getting a current. Apply a current from the C-therm current to the heater. From the heater, this high temperature, spontaneously, as we said, from the second law of thermodynamics, the temperature from hot surface spontaneously go to the cold surface, which is this one. We are going to use it. After that, we can add a weight over the sample to make sure to increase the contact area between the sample and the heater to get accurate result. And we don't know this device accurate or not. You can figure out this just with the 5 minutes you get all the result what you need. So what I'm trying to do, this is the procedure. Turn on the power of the C-therm. Turn on power of C-therm. Open TCI software. There is a software here. This is the software TCI. Going to open. We said OK. So clicking the option beginning the new test. Here this new test. We will choose the new test. Is fairly forward operation. It's very easy to use. It's not complicated. We are going to use the thermal lab. Polymer, a material here, ceramic, foam, high metals, liquid and powder, low metal. We are using the polymer. So with the same thermal lab. Okay, right now contact agent. So we will use a water for the contact area. So what we need to do, we need to add some water here on the surface and place it here to increase the contact area. And that one, we added a thermal grease on this basement, on the brass, to increase the contact area. Here, we are using a water. I'm going to put some water. Here is the water. Place the weight. Make sure in the middle. So right now, start test. You see? Determine the thermal conductivity of given basement, non-metal. We call this non-metal. So we say start test. Okay. So right now, we will collect 5 values of non-metal by using C-Therm computer software. So we will collect 5 values of thermal conductivity for polymer. So each group has a different value of thermal conductivity, approximately the same, but there is a little different because it depends on the ambient temperature, delta T, and here you can see this value infusivity, which is, this is infusivity, depend on the thermal conductivity, depend on density, depend on the specific heat. And the second one, thermal conductivity, directly, this is the first value. It will showing up like it take maybe 50 seconds to get second value. So what I will do, I will go there to check if we reach the steady state or not. Right now, still need time. This is one value. I'm going to move it to show you. You can see here. Gradually increase until reach this point. And you can see this, the surface temperature, 39.9. And still, there is a time. Once we reach the steady state, we stop and save the data. And this is the second value of thermal conductivity. Waiting the third value. Once I finish, I will save the data, take picture, and send it to you. So delta T 1.6, ambient temperature 19.9. So always keep your eyes to make sure there's water, there's no problem here. reading sample, 50-second tick. This right now 1, 2, 3, 4. We need one value. Check this. Thirteen, 12, 11, 10 seconds. So reading sample. Right now 5 sample. Take a snap. This value. I'm going to save it. Yeah, here's the value. I will save it. Okay, right now done. Let's say stop the test. Stop the test. Valid, yes. Close the program. Are you sure? Yes. Close the program. We done. We have the data. Turn off the CTRL. Make sure. And then I'm going to move this one to see if we reach the steady state. You see right now. So here the power, and calculate the power. Power equal volt time ampere. Volt 9.6 time ampere. You see the ampere? 0.94 and you will get the power watt, right? In the text file, you will see in the text file you will see a lot of values start from 0 and then 1 and so on, maybe 1000, 2000, it depends. And then 8 thermocouples, value of thermocouple temperature, T1, T2, 3, 4, 5, 6, 7, 8. And then you see here in the above of the text file, you see the voltage and also a value of ampere. Use these value to determine the power. And also there is no heat losses. And this one you can see this, the white plastic is called, this is for losses. Insulated. Insulated means there is no losses. We assume there is no losses come from inside of linear model to the outside, to the environment, to the room temperature. There is no losses. What does it mean there is no losses? It means we can see here the Q total equal Q input times Q losses. Is there any losses? 0, because this is insulated. This means 0. Therefore, Q equal Q input equal V times I. That's it. So right now I think we reach a steady state. You see there is no change in temperature. 41.8, 41.7, 41.8. You see that there is no change. Almost 0.1. If you see the change for 0.1, that means you reach the steady state. Yeah. We are reaching the steady state. What we need to do, we need to save the data. So we already saved the data here. Let's see. Let me see. Okay. So I will check. Copy. Yes, done for today. Please, if you have any question, you can either call me or email me if you are struggle with your calculation.